This worksheet's going to focus on electron configuration of ions and just ions in general. We're going to start by writing the electron configurations using noble gas abbreviation for atoms, not ions, magnesium and calcium. So using the noble gas abbreviation for magnesium, which is element 12, we want to go backwards in the periodic table to the prior noble gas, which is neon. And we'll begin by writing the formula for neon in the square brackets. And then from there, we are going to pick up the electron configuration. I'm going to add my numbers here to this periodic table. So working on magnesium, we are in row number 3. And that means n equals 3. And we're in the S area of the periodic table. So this is going to be 3s1, 3s2, neon 3s2. For calcium, the previous noble gas was argon. So we'll write that in brackets, and then we will continue the electron configuration from argon. Calcium is in row number 4, so that's going to be the n equals 4. We are still in the S area of the periodic table. Calcium is still in the S area. So this is 4s1, 4s2, 4s2. Question number 2 lets us know that atoms are either going to gain or lose electrons to achieve the electron configuration that matches the nearest noble gas on the periodic table. Not necessarily the same noble gas that we would use for the electron configuration noble gas abbreviation. Sometimes it is, sometimes it isn't. So the first thing we want to think about is which noble gas is closest to magnesium. And with that, we're looking at the atomic number. So the atomic number of magnesium is 12. Going over to the noble gases, we want the noble gas that has the atomic number closest to 12. That is going to be neon. It is the same as what we used for the abbreviation for the electron configuration. So for magnesium, the closest noble gas is neon. And then for calcium, calcium's atomic number is 20. Again, we want to find the noble gas that has the atomic number closest to 20. That will be argon. So for calcium is argon. So this means that magnesium is going to either gain or lose electrons until it has an electron configuration that matches neon, and calcium will do the same until its electron configuration matches that of argon. So for writing the electron configuration of the ion, I'm just going to write Mg ion. Its electron configuration is going to be that of neon, which seems kind of like a cheater way to write it. I mean, we've lost these electrons and got down to an electron configuration of neon. Almost seems like we should probably just write the electron configuration out. For neon is 1s2, 2s2, 2p6. And then for the calcium ion, we said that its electron configuration is going to match that of argon. And again, it seems kind of cheatery to just write argon in brackets, although there isn't anything wrong with that. That is acceptable. It just feels like cheating to me. So there's the electron configuration for argon, and that is also the electron configuration for the calcium ion. How many valence electrons are lost when magnesium or calcium forms an ion? So if we're going to be comparing the electron configuration of the magnesium ion, comparing that to the magnesium atom, we can see that what we're losing are those 2 electrons in the 3s orbital. And then for calcium, again, what we're losing are the 2 electrons in the 4s orbital. So this one loses 2 electrons, whether it's magnesium or calcium, it's losing 2 electrons. What is the charge on this ion? When an ion loses 2 electrons, its charge is going to be a positive 2. Remember that electrons are negatively charged. So as the electrons are removed from an atom, as it loses negative charge, think of that as like subtracting a negative number, that creates a positive charge on the atom. Every electron that we lose results in a magnitude of 1. So if we're losing 2 electrons, it's going to have a +2 charge. The ion will have a +2 charge. If we lost 3 electrons, it would have a +3 charge, etc. All right, let's try this for a couple of different elements. Write the electron configuration using the noble gas abbreviation for oxygen and sulfur. So using the noble gas abbreviation for oxygen, we want to go backwards to the last noble gas, which was helium. And then we work our way forwards from there. After helium, we have, we're in the 2s area, so we have 2s2. And then over here, these all here are the p electrons still in the 2. So these are 2p, 1, 2, 3, 4, 2p4. 2p4. For sulfur, which is right here, the previous noble gas is neon. And then continuing from neon, we're going to be right here. We're going to be in n equals 3, and the s electrons, there's 2 in the 3s2, and then we continue over to the 3p's. These are the 3p's, and we have 1, 2, 3, 4 of those, 3p4. Which noble gas is closest to oxygen? Remember, we're not necessarily going to pick the same noble gas that we did when we used the noble gas abbreviation. We want to look at oxygen, its atomic number is 8, and we want to find the noble gas that has an atomic number as close as possible to 8. So that's going to be neon. The noble gas closest to oxygen is neon. And then for sulfur, atomic number of 16, we want to find the noble gas with the atomic number closest to 16. That's going to be argon. So it's the same noble gases that we used for the magnesium and the calcium. Now what we're going to do is write the electron configuration of these ions. For the oxygen ion, I'm going to, like I said before, it feels funny to just straight up use the noble gas abbreviation. What I'm going to do for oxygen, I'm going to take the oxygen atom using the noble gas abbreviation, so helium 2s2, 2p, but this time to write the electron configuration of neon, actually I think that might be confusing. I'm just going to write out the electron configuration of neon, 1s2, 2s2, 2p6. We've already done that up here, right there. And then the same thing for sulfur. Sulfur, we decided, is going to match the electron configuration of argon, which we've already written up here. 1s2, 2s2, 2p6, 3s2, 3p6. So again, these are the electron configurations of these oxygen and sulfur ions. So when they ionize, this is what their electron configuration looks like. On the next page, it's going to ask us how many valence electrons are added when oxygen and sulfur forms an ion. So if we take a look at this, focusing first on the oxygen, we can see that the changes are taking place in the 2p orbitals. Instead of having 4 electrons out there, now we have 6. And for sulfur, the change is taking place in the 3p orbitals. Instead of 4, we now have 6. So that means that we added 2 valence electrons added when these formed an ion. What is the charge? It's going to be a -2. Remember, electrons are negatively charged. So when you add them to an atom, the ion that's formed has a negative charge. So there are actually some trends that we can translate over to the periodic table, which I'm going to do. So we saw with both calcium and magnesium, those when they ionized, they formed +2 ions, and that's going to be true for everything in that column on the periodic table. And then also we looked at oxygen and sulfur, those formed -2 ions. That will be true for everything in that column on the periodic table. This is totally related to the number of valence electrons that are in these different atoms. For everything that's in the first column, all of those elements, they all form +1 ions. Now hydrogen is a little bit weird. Hydrogen is actually capable of forming either +1 or -1. I'll talk about that in a bit. And the guys that are in this column right here, they like to form +3 ions. Nitrogen and all of its elements down that column, they form -3 ions. Fluorine and chlorine and all those guys like to form -1 ions. These elements in this column and this column, they actually just don't even like to ionize. And the transition metals just do all kinds of crazy things. So we don't have any trends down there. But this is a really nice trend. As we go across the periodic table from left to right, I like to say +1, +2, +3, nothing, -3, -2, -1, nothing. And it's a really nice and easy thing to remember. So we're going to use that to help us fill out this table of different types of information about ions. So on this table, we have a variety of different information, and we're just going to fill the rest of it out. Looking at this very first row, it's telling us The name of this particle is oxide. Whenever you see that "ide" ending, so when an element's name has been changed and the ending is now "ide," that means that it is an anion, which is another way that we say just a negatively charged ion. So anything that ends in "ide" is an anion, and anything that doesn't end in "ide," like this one, is a cation, a positively charged ion. Whether it's a cation or an anion or an atom, it's always going to have the same number of protons. That's never going to change. That's what gives it its identity of oxygen or oxide. So 8 protons, that's always going to be the case. Oxygen is in the column of elements that form -2 ions, so we know that the charge on this is a -2. That's just what it does. When it has a -2 charge, that means that it has 2 more electrons than protons, and the symbol that we use to indicate that is the atomic symbol with the charge in the upper right-hand corner. Let's try that for the next one. This says the sodium ion. Sodium is element number 11, so that means that's how many protons it has, whether it's an atom or an ion. The sodium ion has 10 electrons. It has 1 more proton than an electron, which means it has a +1 charge, +1 charge. The symbol for that is going to be Na. We're going to write the charge in the upper right-hand corner. If the charge is a +1 or a -1, we typically just write the plus sign instead of +1 or the minus sign instead of -1. Next we have nitride. Notice that we have that "ide" ending, so that means that this is nitrogen with a negative charge. So this is a nitrogen ion. Here it is. The question wants us to fill out, first of all, how many protons do we have? That's coming from the atomic number, 7 protons. Now from the symbol here, we can see that the charge on this guy is a 3-. It's there in that upper right-hand corner on the symbol. 3- means that it has 3 more electrons than protons. 7 protons plus those 3 extra gives us 10 electrons. Notice this trend. Look at all these elements that have 10 electrons. That's not like a coincidence. Remember that these guys are ionizing so that they have the same number of electrons as their nearest noble gas. All of these elements are ionizing so that they look like neon. Let's see what we have next. We have an element that has 20 protons. So if we go to the periodic table, that's going to tell us what element that is. That is calcium. Calcium is a positively charged ion because it's in the +2 column, so it's calcium, not calcide or something like that. Also, we can tell that it's positively charged because it's telling us that it has 20 protons and 18 electrons. So that means it has a 2+ charge. The protons, which are positively charged, are outnumbering the electrons, which are negatively charged. The symbol for this, we're going to write the symbol for calcium, and then in the upper right-hand corner, we write the charge, 2+. Next element, we have 35 protons. Let's find that guy. 35 protons is bromine. Notice over here it's giving us the symbol for bromine, and we can see that it's pretty tiny, but there's a negative charge on there. So that means that this is a negatively charged ion. Its name is not bromine anymore. Its name is bromide. I should call this one calcium ion. Bromide with 35 protons, and it has a charge of -1. So that means it has 1 more electron than a proton. Next, we have something with 26 protons, which is iron, and it's telling us that it has a +2 charge. So that would mean that it has more protons than electrons by 2. 26 protons, 24 electrons gives us a +2 charge. This would be the iron ion. Because for transition metals, because they form all different types of ions, sometimes we would actually indicate that it's the iron ion that has the +2 charge. And if we did that, we would say it's the iron 2 ion, like that. That's not really necessary for you to worry about today. We'll just call this the iron ion. And the symbol for this, we're going to write the symbol for iron, and then we're going to write the charge 2+ in the upper right-hand corner. What do we have next? We have an element that has a charge of +1 and 0 electrons. So how many protons would that be? That would be just 1 proton. Now this one is kind of funny with the whole 0 electron thing. 1 proton and 0 electrons that's the only way that we can get a +1 charge. And so you might be wondering, is that even possible? Could you have something with 0 electrons? Yeah, obviously you can, because we're writing it down right here. So what is that element that has just 1 proton? That is hydrogen, H+. Interesting piece of information, the hydrogen ion, H+, is oftentimes nicknamed or referred to as the proton because that literally is all that it is. It doesn't have any electrons. It also doesn't have any neutrons. It literally is just a proton. Okay, so next we have the symbol Ba2+. That is barium. It's a positively charged ion, so we're just going to call it barium ion. From the periodic table, we can see that it has 56 protons. From this symbol, we can see that it has a 2+ charge. That means that it has more protons than electrons. More specifically, it has 2 more protons than electrons, so that means 54 electrons. Next, we have hydride with 2 electrons. Notice that we have that "ide" ending. That means we're dealing with a negatively charged ion, and that negatively charged ion is hydrogen. So this is a really weird situation. This is hydrogen. It's going to be an ion. Hydrogen has 1 proton. If there are 2 electrons, 1 proton with 2 electrons, that's going to be a -1 charge. So that's going to be H-. Now remember when I was labeling these, I said hydrogen could either be +1 or -1. This is, as far as I know, this is the only element that can form pretty easily form either a positive or negatively charged ion. So it's kind of an anomaly that this ion, the negatively charged ion, is definitely the least common form of hydrogen. It's not very common. One of the things that we do know, the electron configuration of hydrogen, it fits in really well with the elements that are in this column, but it also fits in really well with the elements that are in this column. So it makes sense that it follows the trend of the -1 ions as well, and this is something I've talked about before. Hydrogen, we could place hydrogen either here or here on the periodic table, just like helium, we could place it there or over there as well. There isn't really a great spot for hydrogen or helium. So we've got 2 more to go. Next one we have P, that is the phosphorus atom. That has 15 protons. If it has 18 electrons, that's going to give us a 3- charge. And because this is an anion, we don't want to call it phosphorus. We want to call it phosphide. Give it the "ide" ending. Last but not least, 13 protons. That's going to be aluminum. With 10 electrons, that will be a 3+ ion, 3 more protons than electrons. So this would be aluminum ion. And the symbol for that will be Al with a 3+ in the upper corner.